Okay, good morning, Algebra 2. Today's a very exciting day. It's our final lesson of the year. It is a day one, day two, but I'm going to do day one and day two all in one video. And then tomorrow, if you have questions on what's going on, you can come back and watch this video. So I apologize, it might be a little bit longer than normal, but I know most of you watch it on double time anyways. So that's today. Tomorrow is basically going to be going over exactly the same things we're doing today with a separate assignment on it, okay? Our Google Meets will be open for you to ask questions for Mr. Myers and myself. Wednesday is the last day, it's the second to the last lesson today, I'm sorry, or video today. Mr. Myers has the final one on 13.7, and then you got to try on your own. Thursday, we will be doing a live review lesson for your summative on Chapter 13 on June 2nd. Please remember, if Mr. Myers grades you, you will be taking that test from 10 to 10:50. If you're in person, you'll be taking it in room 3333. If you are virtual, you are expected to be logged on to the Google Meet so we can kind of watch you take the lesson. You are required to take it at this time, not any time you want, okay? And if you have me, Mr. Kruger, our scheduled time is from 11 to 11:50. All right, so what we're doing here today, I guess I should have brought that in. We are adding, subtracting, and multiplying and dividing. Dividing was going to be day two, but I'm doing it all in day one. Radical expressions. So what I got here for you is you got 4 warm-up problems that kind of go back. Why don't you come back and simplify these radical expressions? Assume all variables are positive, which means you do not need to worry about absolute values. So why don't you hit pause and give these a shot, and I will be back with the answers. Okay, so back here, what I like to do is I like to see, remember, this is a square root, so we're looking for perfect squares. And I know 54 is 9 times 6, and I further know that the square root of 9 is 3, so that 3 pops out, and square root of 6 has no more perfect squares, so that first one reduces to 12 times square root of 6. Number 2, I see the number 12. Again, these are square roots because it's when it's invisible, there's nothing there, it's a square. I'm breaking 12 into perfect squares, so I know the square root of 4 is 2. 3 stays under the root. Well, I think of, because this is a 2, how many times does 2 divide into 2 evenly? It goes in 1 time evenly and there's none left over. That's why there's nothing underneath that root. How many times does 2 go into 5 evenly? It goes in twice. That's why that's a y squared on the outside. And there's a y to the first left underneath. So 2xy squared times the square root of 3y is my simplified answer. Number 3. I'm coming into cubes now. I'm looking for perfect cubes. So now I'm switching gears. I'm thinking of 8 and 27 and 64 being perfect cubes. And I know 128 comes from 64 times 2. And I know 64 is a perfect cube. It is 4 to the 3rd power. So that comes out. That is my 4. And the 2 stays underneath the cubed root. So I have 4 cubed roots of 2. Number 3, again, looking at cubes. I see 16 actually breaks into a perfect cube of 8 times 2. And then I leave all these numbers the same way. I know the cubed root of 8 is 2. And I know this 2 stays underneath the cubed root because it doesn't come out. I say 3 goes into 4 evenly 1 time with 1 left over. And I know 3 goes into 6 2 times evenly with none left over. That's why that is my final answer. All right? So now what we're going to do is we are going to look at multiplying, okay, our multiplication property here for roots. Well, think about this. Example simplify. Well, I can think of this 2 ways. The square root of 4 I know is 2. The square root of 9 I know is 3. These are still multiplied together, so I have 2 times 3 to get 6. That's one way to do it. Okay. Another way is I got 16. The square root of 16 I know is 4. The square root of 25 is 5. And if I multiply those together there, I multiply them together there to get 20. That is the easiest, well, one way to see it. Or I can think of the square root of 4 times the square root of 9 because they are under the same root. I can take that 4 times 9 underneath that same root and say that's a square root of 36, and I know the square root of 36 is 6. It's just another way to do it. Okay, the same thing here with the last one we got here. I can take that as 16 times 25 because they're both underneath the same roots here. They're both 2's, and if they're under the same root, I can multiply what's underneath there. And I know 16 times 25, well, that gives me 400, and I know the square root of 400 is 20, all right? So this is just really a couple basic examples that we're doing there. And here's your multiplication property. Bottom line, I think of these as belly button rules, okay? Numbers under the radical can be multiplied together. Numbers outside the radical can be multiplied together. So under, these are my innies, okay? These are my innies. And outside, those are my outies. My belly button rules. We got innies and we got outies, okay? It is important. Do not multiply an outie by an innie. What the heck are you talking about? Well, here's an example. Well, A and B, A square root of X times B square root of Y, A and B are outside, so they get multiplied together outside. X and Y are innies, and because they're innie, the same rootie, I can multiply them together as an X times a Y inside, all right? So what we're going to do here is we're going to come here and we're going to do a couple examples. Well, there's a few ways to do things, guys. I want you to know that. And there's always easier ways to do them. That's what makes teaching radicals so fun. I'm going to try to teach you the easiest way for you to do it. Do not become calculator dependent, okay? That's a bad idea. I know the square root of 8 comes from the square root of 2 times the square root of 4, right? Because I know 2 times 4 is 8. Times square root of 32, I know is 16 times the square root of 2. 16 times 2 is 32. Because bottom line, actually, here I'm gonna back this up. I'm gonna take a different approach with you here, and what I'm gonna do, this might make better because these are under the same root. I'm gonna think of this as 8 times 32. Well, because they're underneath there, I'm going to think of 8 as a perfect square of 4 times 2, 32 as a perfect square of 16 times 2. So I know that 4 is a 2, comes outside, times that 4 comes out, that 16 comes out as a 4, and then I still have 2 times 2, and because those are the same roots, this is really 2 times 4 times 2. Okay, because 2 squared, that's really an invisible 4 underneath there. Square root of 4 is 2. So 2 times 4 times 2, I'm going to get 16 is one way to go about that, all right? And the first way, I'm going to come back here and I'm just going to redo that problem the way I was originally going to do it, just so you can see, because I'm going to flip-flop back and forth among these techniques, because the more you do, the better off you get. And I'm thinking of this as my square root of 4, square root of 2, and I'm thinking of this as my square root of 16, square root of 2, and I see this as a 2, this is a square root of 2, this is a 4, this is my square root of 2, and because those are the same roots there, I know these outies are 8, these innies are going to become 2, to get 16. When I'm multiplying the exact same root times the exact same root, the root goes away, excuse me, and I'm just left with what's underneath it. Number 2, okay? And I'm only going to do these highlighted ones. The ones that are not highlighted, you can go on to It's Learning and see the worked out solutions of them. So really, I'm going to see this as, because there's no sum or difference, I can see this as 5 squared, excuse me, times the square root of 3 squared, which really gives me 25 times 3, which gives me 75, is one way to do that. Otherwise, I want to remember, what does it mean to square something? It's 5 square root of 3 times 5 square root of 3. I can multiply my outies. I can multiply my innies to get 75. There's always 2 ways to skin a cat, guys. All right? So what I would like you to do is I would like you to actually hit pause, and why don't you try number 4, 5, and 7, and I will be back with your answers on these just to try to keep this video a little bit shorter than it needs to be, all right? Okay, so number 4, what I'm liking to do here is I like to see that 14 as a square root of 7 times the square root of 2, and I like to see that 35 as a square root of 7 times the square root of 5. I know the square root of 7 times the square root of 7 gives me 7, and I know the square root of 2 times the square root of 5, they're both prime. There's no perfect squares because 2 times 5 gives me 10, and then because they're still under the root, they stay under the root, all right? Now, number 5 comes along, and I just like to take my outies, my 3 times 2, those are my outies, and then I like to see that 12 as 4 times 3 because I'm seeing a perfect square here because those are 2s, and then 6 actually comes from 3 times 2. Well, I know that 4, that square root of 4 is 2, and I know it takes 2 3s, it takes 2 of the same things to break out of jail and become 1, and this guy doesn't have a partner, so he stays underneath, and I know 6 times 2 is 12 times 3 is 36, and the square root of 2 stays underneath the root. I'm multiplying outies and innies, and some people are saying, well, yeah, Mr. Kruger, I didn't want to do that one that way, so I took 3 times 2 and I got 6, and I did the square root of 6 times 12 and I got 72, and then from there I said, okay, that's 6 times the square root. I know 72 is 36 times 2, and I know that 36 is a perfect square of a 6, so I get 6 times 6, and that square root of 2 stays in there to get 36 square roots of 2, and I did it that way. And you know what? I'm going to say, hey, awesome job, congratulations, you did it right. There are multiple ways to do these. Okay, there's multiple ways to get to the end result. This last one is a little, it's not different, it's the same. But see, this last one, these are cubed roots. And because they're cubed roots, what is underneath the root, I can slam all underneath the root. And what I did was I pulled this 3 here, and I'm seeing this 18 right away as 3 times 6, all right? So I can dump that first 3 right here, and then I'm like, well, there's 6. Well, that 6 is actually that 3 times that 2. So if I take 3 times 3 times 3 times 6, 2, excuse me, it's the same as 3 times 18. And then I just added my exponents here because I'm taking x squared times x to the 5th, and then I'm getting an x to the 7th. Well, from there, because this is a cubed root, it takes 3 of the same to break out of jail. Remember, that root is the jail. And that root stays the same. That's still cubed. Notice this 2 is not going to have any partners to come out, so it stays underneath there. Now, when I run into the variables, I'm looking at this x to the 7th, and I ask myself, how many times does 3 divide into 7 evenly? And 3 goes into 7 twice, evenly, right? And if how many are left over? That means there would be 1x left over. Obviously, I don't need that exponent of a 1. And that last x can't break out of jail because he's not coming with a set of 3. All right? So that is how we multiply. That's our multiplication property. And then we do, let's try a couple challenging ones here yet. Well, if I did this, I would take my outies, and I would put my outies together right away. That's going to give me a 12a. And then I'm going to see these innies all together, all right? And I know 18, because these are square roots. I want to see this 18 as a 9 times a 2. And then that 3, I'm just going to throw the 3 with it. Okay? And then the last thing I'm going to do is I'm going to say a to the 3rd times a squared. That's going to give me times a to the 5th power. Well, from here, I'm going to have my 12, my a, and I do this all mental math. And it's really 12 times a, right? So I'm going to just show that. 12 times a. This 9, I know the square root of 9 is a 3 out of jail, right? And then I'm going to have a square root here yet. And I know nothing here comes out, but I do know 2 times 3 is 6.
And then I'm going to say, how many times does 2 go into 5 evenly? Well, it goes in evenly twice, right? 2 times 2 is 4. So that's going to give me an a squared, and there's going to be one a that is left over underneath there. So the last thing I'm going to do is I'm going to take my outies, and I'm going to multiply my numbers. Well, that's 36. A to the first times a to the second is a to the third, square root 6a. And that is my end result for that one, all right? Now, the next thing we're going to be moving along here is we are going to be adding and subtracting. So we might need a calculator to check our ideas. We don't, okay? I know the square root of 9 is 3, plus I know the square root of 4 is 2. So the square root of 9 plus the square root of 4 should equal 5. Notice, that is a little different. If I added the numbers underneath here, don't think that's the square root of 13, because it's not, all right? I know the square root of 9 is 3. I know the square root of 4 is 2. And if I add those two square roots, those two perfect squares together, I will get 5, okay? Well, what is the square root of 5 plus the square root of 5? Notice I have no perfect squares there. But these are like radicals. So I'm thinking I have 1 square root of 5 plus 1 square root of 5. That's going to equal 2. And they are still called square roots of 5. I need to look at these like terms, all right? Well, what happens if I take the square root of 3 plus the square root of 7? Well, that's going to give me the square root of 3 plus the square root of 7. Okay? I cannot add the numbers underneath those radicals. I can only multiply when that sign is between there. The only way to add things is to add them as like terms. These are square roots of 3. These are square roots of 7. This is like an x. This is like a y. You can't put x's and y's together. So because they're not like radicals, I cannot put them together. Well, example 4, we're going to look at some cubed roots. They're the same thing. What is the cubed root of 8? It's 2 plus what's the cubed root of 27? It's 3. So those two, when I add them together, they should equal 5. So what do we get here? Well, your property is, in order to add and subtract radicals, the radicals must be, quote unquote, like each other, like terms, all right? If they are like radicals, meaning the same number under the same radical, okay, all we do is we add or subtract whatever operations between them, the coefficients in front of the radicals, okay? Now, there's this little thing down here in the red. Sometimes we have to simplify the radicals like we did a couple lessons ago to see if they are like radicals, to see if we can add them together. Well, here's an example. What are you talking about? Well, if I have a square roots of x plus b square roots of x, notice they are both square roots of x, so I could take my a plus my b, I could add the numbers in front, and I would have a plus b square roots of x. Well, that's a little wonky to think about, but let's just take a little gander here at number 1. Well, if I have 3 square roots of 7 and I want to add 4 square roots of 7, that radical is like that radical, which means I'm going to have 7 of the same radicals after I add them together, right? Well, how about number 2? Well, check it out. A square root of 3 is not like a square root of 27. They are different, therefore I cannot add them together. However, this is a negative 2 square root of 3 plus this 3. That 27 is really, excuse me, 9 times 3. Check it out. Perfect square. That's going to come out and multiply with that 3, so I really have negative 2 square roots of 3 plus 3 times 3. That's 9 square roots of 3. Now they're like radicals. And what's negative 2 plus 9? That's 7 square roots of 3. But notice, I cannot put them together, okay? It's illegal. I can't put them together until they are like radicals. They need to be exactly like each other. So why don't you try 5, 6, and 8, and I'm going to come back and I'll have these answers for you and I'll explain them. Give them a shot. Hit pause. Okay, so here I'm back now. Now notice I can't subtract these right away because that square root of 8 and the square root of 18, they're different. But they're square roots. I'm thinking square roots, so I want to pull out perfect squares. So I see 8 is 4 times 2, and I see 18 is 9 times 2. Well, 4 underneath the square root pops out and it's a 2, so it's really 2 times 11 gives me 22 square roots of 2 minus, well, this 9 pulls out as a 3, multiplies times that outside number, so I really have 9 square roots of 2. And if I have 22 square roots of 2 minus 9 square roots of 2, I really have 13, and they are still called square roots of 2. Okay, they need to be like radicals. Number 6, just because there's 3 radicals doesn't mean anything. All 3 of these radicals are square roots. So I'm trying to simplify them because 8, 12, and 2, they're all different. So I'm trying to simplify them. And I know 8 is 4 times 2. I know the 12 is a 4 times 3, and 2 is prime, so I just leave the 2. So I know this 4 comes out, and it's 2 times 2 to give me 4 square roots of 2 for the first one. I know this 4 comes out, and that's really 2 times 5 to give me 10 square roots of 3. And these are already 7 square roots of 2. Well, these are 4 square roots of 2 plus 7 square roots of 2. That gives me 11 square roots of 2. And these are negative or minus 10 square roots of 3. Well, I can't break these 2 radicals down anymore. And they are different radicals. So my end answer is 11 square root of 2 minus 10 square root of 3. And I can't put them together any more than that. And my calibration is off again, but that's okay. So the last one here is number 8. Don't tunnel vision everything right away, guys. You want to make things easy. Check this out. Those are all cubed roots of 16. So how many cubed roots of 16 do I have? Well, I got 2 minus 1 plus 3. Well, how many does that give me then? Well, I don't know. I think that probably gives me about 4. And they are cubed roots of 16 minus 2 cubed roots of 24. Well, these are cubed roots, so now I need to pull out perfect cubes. So I'm thinking, all right, 4, that perfect cube of 16 is 8 times 2 minus 2, and I can see that 8 times 3 in there. Well, what's going to happen? This 8 is going to come out, and it's a 2 times the outside number. This 8 is going to come out, and it's a 2 times that number. So I know 2 times 4 is 8, and that's a cubed root of 2. Okay, and that's minus 2 times 2 is 4. These are cubed roots of 3, and a cubed root of 2 is different from a cubed root of 3, so I can't put anything more together. So there is my final answer. 2 cubed root of 2 minus 4 cubed roots of 3. Or, excuse me, 8 cubed roots of 2. So what are we going to do? We're going to move on here. How about combining addition and subtraction and some multiplication, just for some fun, because that's what we're about, having fun. Well, we know this is distributive property. And when I multiply, I take outie times outie is 2, square root. Any times any gives me 30, times, it's plus, outie times outie is 4, any times, really there's a square root of 1 sitting there, square root of 5, and then I just need to look and say, hey, can I simplify? Is there a perfect square that lives within 30? Is 30 evenly divisible by the number 4, or the number 9, or the number 16, or the number 25? Well, I know as soon as I hit 16, it's too many, because 16 times 2 is 32. There are no perfect squares in there. That means that square root of 30 will not simplify. Another way to check that out, if you want to see something different, is you're all really good at prime factorizing numbers. So if I take 30, that's really 2 times 15, and that's really 3 times 5. So if I prime factorize it, I can see that square root of 30 is really 2 times 3 times 5, and I don't have any 2 of the same numbers to break out of jail. Therefore, it stays where it is, if that makes sense, all right? So what am I going to get over here in this next one? Well, number 10. Number 10 is 2 terms times 2 terms. I need to double distribute. That's 6 times 2 times the square root of 5 gives me plus 2 square roots of 5. Then I got to distribute that square root of 5 plus 3 square roots of 5. And the square root of 5 times the square root of 5 gives me a positive square root of 5. Positive square root of 5 gives me plus 5. It just kills out those radicals. Then what do? Well, 6 and 5 are like terms. That's 11. And 2 square roots of 5 plus 3 square roots of 5, that gives me plus 5 square roots of 5. And I can't put numbers and square roots together, so that's what that one goes to. Why don't you give 11 and 12, and be very careful on 12, but give 11 and 12 a shot, and I'll be back. Okay, number 11. I'm looking here, and as I distribute that 3 to the negative 5 square roots of 10, outie times an outie, so 1 times negative 5 gives me my negative 5. And when I'm looking, I'm always a step ahead, guys. So I'm looking, I know 3 times 10, I know that gives me the square root of 30. We just found that before. But I'm thinking of what is the square root of 3, and I'm saying times, I'm trying to picture that 10 as 2 times 5. So I'm looking for pairs of numbers to take out, and I know that 30 is equal to the square root of 2 times 3 times 5, and there are no sets of 2 to come out, so that's why I gave that a 30 right away. But when I distributed the square root of 3 to the square root of 6, I'm picturing this guy as 3 times 2. So to show you, I'm really looking at the two square roots where I have this first square root of 3 is here. This out of the 6, that 3 comes from there, and that 2 comes from there. So I'm looking to see, hey, I have a pair that's going to break out of jail to give me that 3, and that 2 doesn't have a partner, so he stays underneath there, and I know the square root of 30 is different from the square root of 2. All right? Now, over here, I said be careful with number 12. And I said be careful for number 12 because if you're just trying to do that, remember, this addition symbol in here in the middle says I cannot just distribute that squared in there. This does not equal squaring both terms in there. It doesn't mean that. You got to remember what squaring something actually truly means. And what it means is take it times itself. Excuse me. Which means I need to double distribute, which as I come along here, I know the square root of 7x times the square root of 7x gives me my 7x. Square root of 7x times 3 gives me 3 square roots of 7x. Plus 3 times square root of 7x gives me 3 times square root of 7x. 3 times 3 is 9. I combine like terms. I have no other plain x's. Okay? So I only have 7 x's. These guys right here, they're like terms. So I got 3 of them here. I got 3 of them here. So I got 6 total plus 9. And what is left over, none of those are like terms. So that's why I have to circle my answer there and I have to leave it. When I'm adding and subtracting, they need to be like each other to put them together. And if they're not like each other, they cannot be put together. Now, I have these last, 13 and 14. These are very important examples for division, okay? What do you notice here? Hopefully you notice these two sets of parentheses are almost identical. The only thing they differ from is the sign between the numbers. What is going to happen here? Something magical and mystical happens. Watch when I double distribute. 7 times 7 is 49. 7 times negative square root of 3 gives me negative 7 square root of 3. And when I take the square root of 3, positive square root of 3 times 7, I get positive 7 square roots of 3. And when I take a negative square root of 3 times a positive square root of 3, a negative times a positive is going to give me a negative. The square root of 3 times the square root of 3 is 3. And now watch, like terms, 49 minus 3 gives me 46. And negative 7 square roots of 3 plus 7 square roots of 3, hey, those wipe each other out. And when I multiply these special sets here, I don't have a root left. I just get a number. These are called These are called conjugates. Same numbers, opposite sign. And when I multiply conjugates, special things happen. 4 times 4 is 16. 4 times 5, square root of 5 is plus 4 square root of 5. Negative square root of 5 times 4 gives me minus 4 square root of 5. And a negative times a positive gives me a negative, and the square root of 5 times the square root of 5 gives me 5. 16 minus 5 gives me 11. 4 square roots of 5 minus 4 square roots of 5, those cancel each other out, and I end up with just 11, okay? Very important examples for the last problems we do in division, all right? So we're going to move along here. Division. Well, looks like we're there, yeah, well, we're here. Well, there's 2 ways to skin a cat, guys, you got to know. Notice the numerator's under a root, the denominator's under a root. Well, when I'm looking at this, I know what the square root of 36 is, that's 6. I know what the square root of 4 is, that's 2, and they pop out. And what is 6 divided by 2? It's 3. Well, if the numerator and denominator are both underneath the same root, I can see the whole fraction underneath the root. And when I see a fraction, guys, just remember I can reduce that. How many times does 4 go into 36? 9 over 1. So that is really asking you, what is the square root of 9? It's 3, okay? So your division properties, just remember, when you're trying to simplify a fraction, innies can simplify with innies, outies can simplify with outies only. You cannot simplify an innie with an outie. What do you mean? Well, if I had 2 over the square root of 6, this is not equaling to 1 over the square root of 3. I cannot reduce an outie with an innie. That is not legal, okay? So don't do it, please. Well, let's check a few of these out. Well, let's see here. Well, let's go. What are we going to get? What are we going to get? Well, I can think of, okay, now that's not a perfect square and that's not a perfect square. So I'm thinking maybe I want to see the whole thing underneath there. Does 3 go into 27 evenly? Well, you bet it does. It goes in there exactly 9 times. Well, what's the square root of 9? It's 3. So sometimes when I have separate radicals, I want to see them underneath one radical. Other times, when I see one whole fraction underneath the radical, and check it out, it doesn't reduce, does it? I might want to see that as the square root of the top over the square root of the bottom. Well, what is the square root of 81? It'd be 9 over, what's the square root of x to the 6th? Well, how many times does 2 go into 6 evenly? Maybe 3 times, and there's none left over, so that is what it reduces to. All right? Well, what happens when I look at number 3? Well, the same thing. Nothing inside this fraction reduces, so I'm just kind of looking 64 x to the 5th over square root y to the 6th. And I'm going to look at it. Well, what is the square root of 64? It's 8. And how many times does 2 go into 5 evenly? Twice, with 1 left over. And how many times does 2 go into 6 evenly? Maybe a y to the 3rd. And I am simplified, okay? Why don't you give 4 and 5 a quick try here? So I'm just showing you my thought process here. And because these are both, the numerator and denominator are both underneath the same root, I can see the whole fraction underneath the same root. So that I can look at that fraction and say, hey, I can reduce that fraction. And when I reduce it, sometimes I want to see it split back in the top with the root of the top, the root of the bottom. Do I have to do this? No. If you see these are the same roots, that means you can reduce the numbers underneath and you can jump straight to here. Okay? And then from here, you know the cube root of 27 is 3. And you know the cube root of 8 is 2. So number 4 is just 3 over 2. Now number 5, same thing. Because these are both square roots. If they're the same indexed root, I can put the whole fraction underneath the same thing. What do you mean? Well, if I had the the square root of 5 over the cube root of 10, I could not see these underneath the same root. They are a different index, therefore I could not reduce the innies because they are of a different index, all right? We're usually not going to throw that at you too much, but you got to be careful with it, right? So what I'm doing is I'm seeing these are both squareds, so I want to see the whole fraction underneath that one squared. And when I do that, I see I have b's in the top and I have b's in the bottom. And those b's will reduce, well, there's 4 more in the top. And just so you know, yeah, that technically is all over 1, but just remember when it's over 1, I don't have to write the over 1 because my fraction's gone. And then I'm just looking, because that's a square root, well, I know the square root of 5, there's no perfect squares, that's why that stayed in there. 2 goes into 4 evenly twice with none left over, that's why all the a's came out. B goes into 4 evenly again, so that's why there's a b squared, and the square root of c squared is just a c, all right? So, things you cannot have under radicals. You need to remember these little buggers too. And I'll be honest, by the time you hit calculus, if you do, some of these rules can be broken, and I'll explain why at that point if I have you in calculus, and if not, hopefully your college professor will explain it to you. But simplest form conditions, you cannot have negatives under radicals, okay? You cannot have perfect squares or cubes or fourths. It depends what index root you started with. You can have perfect nothings underneath the radical either. And number 3 is the hardest one to remember for some people. It is illegal to leave a square root, cube root, any index root in the denominator of a fraction. They have to come out. There's a special way to get them to come out. So let's take an example. Let's look at number 6, 7, and 8. And then I'm going to have you try a few. But 6, 7, and 8, well, they're all underneath the same root. So this is, notice that fraction doesn't reduce. So I'm really going to look at this as the square root of 3 over the square root of 2. Well, I have no perfect squares in there, but check it out. I have a root in the denominator, and I can't leave that there. So what do I need to do? Well, what I need to do to get that root out, I'm going to multiply that root by itself. Now check it out. The square root of 2 over the square root of 2 is 1. That's a beautiful thing of fractions. I can multiply. There's an infinite number. There's an infinite number of ways to show the number 1. And something times 1 is itself that. But the beauty is, if I take the square root of 3 times the square root of 2, well, I get the square root of 6 over the square root of 2 times the square root of 2 gives me just 2. And now I got to look at, well, my radical's out. I have no perfect anythings in there, no negatives, so that is going to be the square root of 6 over 2. Well, again, when I look at number 7, 5 over 8 does not reduce, so that's looking at square root of 5 over the square root of 8. Well, look at this. That has a perfect number underneath it. So it's really the square root of 5 over, I'm picturing the square root of 4 times 2, okay? And the reason I'm picturing that is so that I can see this as the square root of 5 over 2 times the square root of 2. Problem is, I'm not allowed to have a square root down there. How would I get that square root of 2 out? I multiply it times itself. And then when I come to the top, I have the square root of 2 times the square root of 5. That gives me the square root of 10. And on the bottom, outie times outie, any times any, is going to give me the square root of 10 over 4. And now I have no root in the denominator. I have no perfect squares underneath the root. I have no negatives underneath the root. So I am done-zo, and that is simplified. All right? Number 8. Well, that's really looking at x, square root of x over square root of 3, because x over 3 doesn't reduce. I need to extract my square root out of the denominator, so I multiply both top and bottom by the same thing, so it's 1. And that is the square root of 3 times the square root of x. That's the square root of 3x over square root of 3 times the square root of 3. That's just 3. Boom, done. No, you may not reduce the 3's. The bottom three is an outie. The top three is an innie. You may not simplify outies and innies, all right? Keep that straight. So what are we going to do here? Why don't you give 10 and 11 a shot, and I'm going to hit pause. I know this video is getting long, but remember, this video is covering today and tomorrow. And so remember, you might be doing these a different way, getting the same answer. That's totally okay. You got to remember, Mr. Myers and myself have done millions of these things, and we kind of know the path of least resistance just by looking at a problem. But when I'm looking at number 10, no roots in there, so I got to extract that root out of the denominator. So I multiply by my special value of 1 to get rid of that root in the bottom. But then notice, I can see that root in the bottom, okay? That outie with that outie will reduce. 5 goes into 10 twice, so my outies reduce, and that just gives me 2 square root of 15, all right? When I look at 11, personally, I could throw this underneath one root, and I could try to reduce this, and I could, because if I did, I could look at this as the square root of 8 over 10, right? And then, or 100, and then I could reduce that each by 4 and see that as the square root, big square root of 2 over 25, and then that's going to make me see that as 2 over square root of 25, which bebops me right here. But what I chose to do is I chose to say, well, I'm going to break this out and pull them at perfect squares. And that is a perfect square, so that's 10. 8 is 4 times 2 to give me my 2 radical 2. And then my outies reduce, and I get my square root of 2 over 5. All right? There's lots of ways to do these. Lots of ways to do these. So what we're going to do is I would like you to hit pause and give these 3 a try. And after these 3, there's only 3 more, but the last 3 are tough. All right? They're much more tough than these. Give them a shot. I'll be back. Okay, now just note right away, you may not reduce those b's because one is in, one is out. That is illegal. So the whole top is out. So what do I need to do? I need to extract that root out of the denominator. So I multiply by square root of 5b over the square root of 5b. And then I really wish I would have changed my colors here like I had been consistent, but I didn't. But when I multiply these two, I get the numerator. When I multiply these two, I get the denominator. And now check it out. Now I have 2 b's that are outies that reduce, and I'm left with 2 times the square root of 5b in the top over 5. All right? And when I look at number 16, I know the square root of 4 is 2. That equals 5 square root of 3. Well, I got to get that square root of 3 out of the bottom. So I multiply by it, the same thing, the square root of 3 over the square root of 3. Well, 2 times the square root of 3 is 2 root 3. Times 5 square root of 3 times the square root of 3. Well, what I'm picturing is I know when I multiply these two, I get 3. That's times that 5. That's where the 15 comes from. The 2 and the 15 do not reduce, so it is 2 square root of 3 over 15. Number 17. I can see these are both the exact same indexed root. So I picture them all underneath the same root. And I can see I can reduce my numbers, and I get 5 over 1. I can see there are 4 more x's in the numerator, and there are 2 more x's in the, or 2 more y's, excuse me, in the denominator. So then I see that new fraction. After I see the new fraction, I'm like, oh, they're under the same root. So I put the top root there and the bottom root there. I know there's no perfect squares in the 5. That's why the 5 stayed underneath. And I do know the square root of x to the 4th is x squared. And I do know the square root of y squared is y, and x's and y's do not reduce. That is why that one stayed where it was there. Last 3 examples, okay? So recall from the important examples I said. Notice there's something different going on here. I cannot, if I have a sum or a difference in the denominator, see that plus? This has got a minus, the last one's got a minus. Okay? It's not as easy as just trying to go like this. You get into tunnel vision, guys, and you're like, oh, I know how to get that square root of 2 out of there. I'm just going to multiply by the square root of 2 over the square root of 2, which is 1. Well, if you did that, here you're going to get 2 square root of 2 in the top, And then I have to distribute that. That gives me 3 square root of 2 plus 2. And because that is a factor with that sum, that is a factor, I cannot reduce anything top and bottom, and all I have done is moved where my square root of 2 is nested. So this is a different technique when there's a sum or a difference in the bottom. Hence is why my very important examples before, what do we want to do? We want to multiply this by something that when I take, what do I take 3 plus the square root of 2 by to get rid of the square root? It's conjugate, 3 minus the square root of 2. And if I multiply that times the bottom, and I get that on the top, that is just the most disgusting form of 1 you've ever seen. Same number over the same number. Then, I'm going to say 2 times 3 is 6. 2 times negative root 2 is negative 2 root 2. And on the bottom, I'm going to say, hey, there's 9. There's minus, not plus, Kruger. Come on. Oh, boy, I got a little rogue there. That's 9 minus 3 square root of 2. And then I got to distribute here plus 3 square root of 2. Square root of 2, positive, negative is minus 2. And then I'm like, ooh, isn't that nice? I get 6 minus 2 root 2 in the top. And I see 9 minus 2 gives me 7. And these guys get rid of my root. And when I try to reduce this, guys, notice the top, there's a common factor of 2 in there. And I have a 3 minus root 2. And I have a 7. Notice that 7 will not reduce with that whole set of parentheses, nor will that 7 reduce with the 2. Therefore, that is my final answer. If I'm going to try to reduce, these outies must reduce all by the same number. It's what I call happy bunny ears, okay? And why don't you hit pause, give 19 and 20 a quick shot. Okay, first thing I notice is I have a difference in the bottom. So the only way to get rid of that square root is to multiply by its conjugate, which is the same number 2, the same number square root of 3, opposite sign in the middle, because then when I do my double distribute, I see my outer and inner terms are going to go away. And I say 5 times 2 is 10. 5 times the square root of 3 is 5 square root of 3. I can double distribute here. And when I double distribute, I collect my like terms. I get 4 minus 3 is 1. I get 2 root 3 minus 2 root 3. I see those cancel out. I wouldn't want to leave it over 1, so I rewrite it 10 over root 3. Now, all of this is too much for me. I usually don't do that. I'm going to show you what I do. So, when I get to number 20, I'm like, ooh, I have 2 terms down there, so I have to multiply by the conjugate. And what's going to happen is, when I multiply by my conjugate, guys, we know these middle terms there are going to drop out. So I'm going to distribute the top, and then I know my outer terms and my inner terms, I know they're going to cancel each other because I can see they're the same thing, opposite sign. That is the whole point of understanding the mathematics you're doing. So when I do this, when I know it's a conjugate, when I know they're going to fall out, I'm just taking 7 times 7 to get 49. My negative root 13 times my positive root 13 to get my minus 13. And on the bottom, when I combine those like terms, I get 36. Now the last thing I need to do is I need to see, do these outies, can I take the same exact number out of all of those? All 3 of those are divisible by 2. So I'm going to divide them all by 2. And I'm going to get 35 plus 5 root 13 over 18. And are all those outies divisible by the same number again? And the answer to that is no. Therefore, that is our simplified answer. I apologize for the 50-minute video, guys. However, remember, it's today and tomorrow. You can fast forward it, whatever, to time it. But I want to thank you guys for a good year. Hopefully, come by and see me next year when you're walking through in pre-calc. If you need any help, I'd be happy to do that. Have a great summer. Please ask questions on Tuesday. I'll have my meet open. Mr. Myers will as well if you have questions on Tuesday, Wednesday, or Thursday. And remember, our final test is going to be June 2nd, 10 to 10:50 for Mr. Myers grading people and 11 to 11:50 for Kruger's grading people. And we will use the same exact Google Meet link that you hook onto right here to get in there and see the test. And there's going to be 2 portions of it. Hey guys, have a great day, have a great summer, and reach out to us with any last questions you have before the end of the year. Bye.